Okay. And hello, everybody. So I'm from Trier University, and we have a code for this finite element approximation of non-local operators for a specific case. We will talk about this later. So I prepared some kind of interactive presentation for the code where we can also look into some example how it works. But I would be interested in what your background is. So if there is anybody who is actually interested in using it, the code, or what your background is in programming, and so on. So for me to have a feeling what you want to know. Maybe you can write in the chat so I can see as soon as I find the chat.
I can keep track of it, Manu, and I will.
Yes, I see it. Yeah. I see it.
No worries.
So maybe you can just write to give me an impression of if you actually plan to use that code, or some code at least for find elements, or if you just hear out of interest. Yeah.
I don't see anything for now.
No, nothing happening.
Let's assume we have a mix of people.
Yeah. Okay, we skip this. Yeah. So I'll just give you that presentation. It maybe takes 20 to 30 minutes, so I didn't plan to take the whole time. And then we would have some kind of break, some time where we could try to run the code on your computer if you want. So that would simply work over a Docker image. So there's no installation of prerequisites or something like that required. You can just run the Docker image, and we can have this tutorial, for example, what you see now, you can execute it on your computer, laptop, whatever, and can have a look at the examples. And there are more examples prepared than the one I show you here. So you can try to look at the other examples, try out other options and something like this to investigate this specific function. Okay, so that's just the structure of the whole thing. So first of all, there will only be this talk. Then there will be a small break, so we have time. And if you want, we could then go on and try out the code itself in a hands-on kind of session, if you want. I mean, I think this is we are rather flexible here, and I just want to give you some kind of insight. Okay, I see also some answers there. Okay, cool. So there are people also planning to develop a FEM code themselves. That's very nice. So then maybe you're interested also in some some ideas which we put into that one. The thing is, the link to that repository is given in that non-local codes abstract, which Marta showed you already. So you can find everything there. Good. Okay. Fine. So the problem is the following. You see it there. We have some domain omega tilde, which is part of R2 in our case now, compact, and then we have within that set we have a set omega, which is open with respect to that set. So the complement of that set is, we call it gamma. That's the place where we could usually set, for example, Dirichlet boundary conditions. And then the operator looks as follows. So L delta of u minus L delta of u is given as this integral there with the kernel c of xy, which is applied to the function u of x. And it's evaluated on that set omega tilde, where we intersect always. Okay, that we put here. We put here a b of x, where we intersect with the interaction domain b delta of x. Okay, so the interaction is only restricted to a certain domain around interaction horizon around x. Okay, So then there's a weak form. That is what we assemble actually, and we could solve with that system basically a Dirichlet type problem, for example, which you see here, where we have a forcing term f on omega and some kind of Dirichlet boundary data on the non-local boundary gamma. Okay, if you want to build and install the code, you have to do all, make sure you have all the prerequisites set up. It's all explained here on that page. There's a README file, and then you can look through all those things, install them, and then if you have everything set up, you can basically build the code. It's a Python code, so there's a Python interface in order to make this code available from Python, and behind that there's a C++ implementation. So we use that force here in the building process to make sure that the build process is not skipped if you have changes in the C++ code which are not seen by the Python interface. It's not so important, but you find all the descriptions there for the installation in that README file. Okay, and there's also a description for how to pull the Docker image. Okay, so now let's talk about the details. So basically, this whole code is only one function which takes some input values and gives you the stiffness matrix. That's basically it. It's only one function, basically. And the first part of the input values is, of course, the domain. And we just have to agree on some conventions, how the mesh translates to the degrees of freedom. So we talk about this here. What we do here is in that code, we are given labels for the interior omega and for the Dirichlet boundary, the non-local Dirichlet boundary. And the positive labels are for the interior. Maybe I have a picture here. Yeah. And the negative labels are for the non-local boundary. If an element has label 0, then it's ignored. So you look at the first line here in that code. So there's some kind of mesh produced. I think this is from Gmesh now. And this basically needs vertices, elements, and some labels for the elements. And then you see that we generate from that triple, we generate somehow the mesh. The mesh in our case is much more also containing those degrees of freedoms kind of information, which would usually be a different thing, but I just dumped everything into this mesh dictionary. So we generate the mesh, and now you see here how this looks. Okay, so it's black on the outside, so this is the Dirichlet boundary, and then in the middle we have two disjoint domains, one with label 2 and the other one with label 1. Okay, that's it. Fine. So now, of course, in case of continuous Galerkin, we have to somehow agree on how the elements, the labels of the vertices translate to, the labels of the elements translate to the labels of the vertices. So the positive labels of vertices, again, are those which belong to omega. So, and those are exactly the unknowns in the continuous Galerkin case. So there it's the same thing. And again, the negative labels belong to the Dirichlet boundary. And we somehow agree on that if a set A is closed, then this means that the vertices X of elements E, so the vertices of that element belong to the same label. So that is somehow the convention we take here. For example, omega tilde is closed in R2. So that means that those outer boundary nodes of those two disjoint subdomains, which had label 2 and 1, they also are unknowns. So there's no label 0 or something. This is not set to 0, but they are also unknowns on that boundary. Similarly, the Dirichlet, non-local Dirichlet boundary is closed. So here we see a different mesh where there's a hole in the middle, and then it's immediately connected to its non-local Dirichlet boundary, the normal case actually. And there you see that the outer Dirichlet boundary is black, so the labels are Dirichlet labels there. And then you see that the vertex labels are also in that sense that the vertices which lie on that local Dirichlet boundary, they are also belonging to that Dirichlet boundary. That's just because of the closeness of the Dirichlet boundary within omega tilde. Okay, so that's somehow what we decide to do, and we therefore derive in that way the element, so the vertices labels from those labels of the elements, element labels, and vertices. Okay. Okay, that's basically the very basic ingredients of the domain, and what we need for that is, again, some vertices, elements, and element labels, wherever you get them from. Okay, that could also be some other simple meshing tool which you want. Of course, element labels are user defined. You can do whatever you want there. Okay. If there's no negative element label, then we are in this kind of Neumann setting. So there's just no Dirichlet boundary. Then you might not be able to easily solve the system, but there's no problem with assembly. You can set it up. Okay, no questions in the chat. Okay, so that was the first part. Now there's one more thing about the domain. So how do we find actually the elements which interact? So in general, in case of non-local operators, it's not only the elements which interact with itself, but elements interact with remote elements. So we have to somehow find those elements which interact. And in our case, what we do is we simply use matrices to set up the dual graph of the mesh. That's quite fast and cheap. And then we have a graph which we can traverse with a breadth first traversal and efficiently find the interacting elements. So that means, like, on the fly in that integration routine, we simply compute the integrals over pairs of elements, EA and EB, and as soon as we find no interaction anymore, we stop the search. Okay, so that happens if you see here, if for no vertex or for no quadrature point x in element EA, there is an intersection with element EB. In that case, there is no interaction anymore. So that's because of the truncation. And then the breadth first traversal stops. That's very nice because this avoids touching all pairs of elements to find neighbor or to construct neighborhood lists. Okay, neighborhood lists are not necessary if you have a mesh. That's somehow the advantage of the mesh. And you have also to see that a neighborhood list, of course, is expensive in the sense that it costs you maybe as much space as the stiffness matrix or something comparable. Okay, so we don't need that at all if you have a mesh, because actually the information is there. However, there's a disadvantage of that technique, namely, it could happen that oh no, I show you a picture. It could happen that the intersection of the non-local interaction set B delta X and the domain is not connected. I show you the picture of the previous slide. Here you see that hole. So if the interaction set is larger than the hole, then the intersection of omega tilde and B delta is not connected for some cases here. And therefore, this breadth first traversal would fail. But what we can do is we simply add some artificial elements which are then traversed but ignored in the integration routine. So I just show you this picture here. So we take some vertex, connect all the lines which are the local boundaries. So this is like one-dimensional lines, connect them with that point, and then we can artificially change that mesh in the sense that every time this search graph is connected. So for this case, but also for more complicated cases, let's say here for a disconnected case, you see that other picture, remember that. So even here, we can guarantee that the search graph is always connected. And still, this is efficient because we do not connect all points with any other point, but only those lines. And you, of course, are also free to do other things here. And that is something, of course, which occurs only in case of non-local. So in local, you don't have that problem at all. You cannot have non-local interaction or disjoint domains or something. It makes no sense. Here, it could make sense, and we also allow for that. Okay, just check if there's any question. Good, fine. So that's the domain. I think that's it. So the next ingredient to this whole function is the kernel. So the kernel function in our case is, as you saw it already, a function c of x and y, and it can also depend on labels. So the labels are here lx and ly, and those are the labels of the elements. Yeah, you heard that already. And the dictionary, it's a Python dictionary with which we set the kernel, contains 4 ingredients, namely the function itself. So that's not the function, it's the name of the function. The kernel has to be pre-implemented in that C++ code. That's maybe also not the most elegant method, but you have this pre-implemented and you just choose the kernel function by the name. Then we also choose the horizon. That's a parameter like delta, like 0.1 or 0.2 or something. And then you have the output dimension of the kernel. For scalar case, you put 1, for matrix value 2 or something like that. That's redundant also. Of course, this has to match the function you chose, but that's how it is. The fractional order is an optional setting. This makes only sense, of course, for fractional type kernels. There you put the order S of that fractional type kernel as an option. Let's see. Okay, so this is how it looks. We start setting this kernel dictionary now, and you see here that we set the horizon to 0.3. Good. So that's the first ingredient. Now we need to know, of course, which functions can we choose. The pre-implemented functions in that kernel are for 2D are the following. So we have a constant kernel. You see that here that's 4 over pi over delta to the power 4. So that is the constant which converges to the Laplacian if we use as an interaction set the L2 ball. Similarly, we have that constant for the L infinity ball. We also can intersect with respect to the L infinity ball. We talk about that later. And we have the linear prototype microelastic kernel. So that is the scalar case. You see the diffusion type kernel here, and also the paradigmatic kind of kernel. So here you see this is matrix valued, and both of them have some kind of singularity there, but it's weak. And then there's also the fractional type kernel. Okay, so the fractional type kernel has a stronger singularity, and all the constants in this case in the pre-implemented kernels are chosen such that for delta to 0, the operator in theory would converge to the local operator. Okay, the last one is an example. That's just so you know the name. That's a test case where we set the kernel to the constant kernel, except if the label of x is smaller than the label of y, then the kernel is 0. So if you have 2 neighboring domains with different labels, then the interaction will only be in one direction, not in the other one. And of course, then this is not symmetric. Okay, so now we want to choose a kernel, and we set the following. So we set the function to fractional. Output dimension is 1, so this is a scalar case here. And we set the fraction s to 0.5. So s is between 0 and 1, excluding, excluding 0 and 1. Meaning, okay, we can also set other s, a negative s here, but I come to that later. or no, we put it now. So this fraction S, it controls integration routine, which is required for singular kernels. And you can use that integration routine also for other kernels, of course. You can also use it if you don't need it. For example, in case of the linear prototype microelastic kernel, which is singular, but it's so weak that you can actually use a regular integration routine. If you want to use that special integration routine for other kernels, you have to correctly set this value. So in case of this prototype microelastic, it would be, I think, minus 0.5 or something. Okay, it would work, but it's not necessary. For the classical fractional type, you set this up, and then okay, and then the fractional routine would work if you set it. Okay, so those are the kernels. Yes, of course, that might not be what you want. So you might want to declare kernels on your own. So for that, you have to recompile the whole code and install the kernel at the specific points. So in that repository, there's a directory called source, and in that you find the models header. There you have to declare your kernel, and that has the following interface. So it's a C++ function, and it takes a double x, so that is a pointer to the quadrature point x. It takes the label of x, it takes the y, takes the label of y, and some mesh. So mesh is basically a class which contains a lot of data and information, has access to that, and it also outputs the value to the kernel value pointer here, the last one. So you have to declare that function and implement that function in the C++ file, in the corresponding C++ file. So whatever you want your kernel to do, you put it there, and then basically you have declared and implemented this new kernel. However, it's not yet accessible, so you want to choose this by your name. You still need to choose the name. So there's one other file called cassemble C++. That's basically the file where everything happens. It's just one big file, and there you find a mapping a string to function pointers. So you take your kernel name and map this to your function, and basically then you can choose from the outside, from the dictionary in Python, you choose that name, and then the function pointer is set to that function, and it executes that function whenever you call it. So that's the way you can use this own kernel. And of course, you have to build and install the whole code again. Okay. So there's no way to do this from the outside. I can maybe also go into detail with the structure of the repository if you want, but I want to skip that now. I just wanted to tell you that there is a way to have your own kernel. It's not completely impossible, but it's not something you can put in from your Python interface. Okay, those are the kernels we can use. Let's see if there's a question. So then everything else happens in the configuration. That's a dictionary conf. So that contains all the elements of the quadrature rules, ansatz space, and those kind of things. So we set that up now together. Let me see. For the integration routine, we always integrate over pairs of elements. So you see the double integral here. And if v and u are, for example, two ansatz functions, then we want to evaluate those integrals as the local contribution to the stiffness matrix. And then we evaluate those contributions on pairs of elements. So EA would be the outer element and EB would be the inner element of that integration routine. Then we want to evaluate that expression in the middle with that kernel C with respect to either the singularity or maybe the truncation. So that means that different pairs of elements, depending on whether they exhibit this truncation, for example, so if they are far away from each other and there's a truncation, then we need another quadrature rule then if we have a singular kernel and the elements are touching. So if the elements are touching and we have a singular kernel, we need special quadrature rules. So there's somehow a switch between quadrature rules depending on the case. So that's the first thing to say here. And one thing I want to note is that we cannot mix that. So the truncations are required for remote elements, and we require those special quadrature rules for touching elements. But if the horizon, if the interaction horizon delta is, for example, 0.1 and the diameter of the mesh is also 0.1, then, so if h is equal to delta, then it might happen that the direct neighbor, or sometimes even the element itself in some cases, might need to be truncated. If you have a singular kernel, a very singular kernel, like the fractional type kernel, then that doesn't work, okay? So in that case, you wouldn't see an error, but the code would overestimate the interaction set B delta. It would take all the neighboring elements also into the interaction set without checking without taking account of the truncation. So for example, if you use a fractional type kernel, you should use 2 times or 3 times h as your delta. Otherwise, there might be an overestimation, okay? So that's just a small note about the integration routines. But okay, we have those 2 cases, and we now want to set up in the configuration the quadrature rules for those cases. First, we start with the truncation. The truncation we have 2 cases in the 2D case. So the first one is the L2 ball, which is possible. So you have there a geometric error of O of h squared with that real triangulation which we implemented there, and you can therefore nicely integrate over kernels which are truncated with respect to L2 balls. So it's called retriangulate. So that's the name of that routine or of the configuration you have to set. If you set this to L infinity, then you get the truncation with respect to L infinity ball. However, you have to also be aware of the fact that that doesn't mean that the kernel matches the truncation. So if you have a constant kernel and you want to observe convergence to the local case, you have to choose the correct constant to match that truncation. Okay, so now what we set is, we set this method to retriangulate. So basically that is, the configuration dictionary has to have an entry called approx balls. So that is the whole, the name of that entry, and then the method is here called retriangulate. So that is the L2 ball in this case. It's a very old name, but yeah, you know it now. Okay, so the next thing is we need to set quadrature rules for those approximate balls. The first thing, so those are the quadrature rules for the outer element EA and the inner element EB. I already told you, you saw the integrals there already. So for all the simple cases like constant kernels, or also for those very weakly singular kernels like the microelastic kernel, it basically suffices that we technically avoid zero division. So that's, in my experience, it was good enough. So you could simply take for those cases for EA a quadrature rule which does not hit the points EB, and then this is okay. It works, at least in my case it worked. And then you simply set that quadrature for the outer elements to some points in weights, and the inner to some points in weights, where here we use a 16-point quadrature in the outer and a 7-point in the inner. So they don't, you never get this technical zero division. That's it. So that's good enough for, of course, for constant kernels, but also for those very big singular kernels. But in our case now we chose the fractional. So then we need a different technique. So for fractional kernels, if the kernels are touching, then we need special quadrature rules. So here, this entry in the configuration dictionary is called close elements. So so for this close element, we need a special rule, simply a special rule. And the name for that is called fractional. So the reason being that the routine needs some information about the exact definition of the kernel, actually. So this routine is tailored to that truncated fractional kind of case. Okay. And the code works as follows. So if we have a singular kernel, like the microtype, prototype microelastic type, or this fractional type kernel, then the code uses the routine which is set in close elements as default in the first layer of the breadth-first traversal. That's another advantage of the breadth-first traversal. We automatically find all touching elements because that's just the first step. Okay. In that first layer, we use that special quadrature which is set here. However, if you do not set that rule, the default for the first layer will be the approx-Ball's quadrature. So again, that is good enough for very weak singularities, but that doesn't work at all for fractional type kernels. So you use that. Here, in our case, we use this one, the fractional integration routine for this kernel. Now we need to set the number of quadrature points in that fractional type quadrature. So the name is a bit misleading. We just set the number of points here. So those special quadrature rules, they basically take, they pull back the integration domain EAEB, which is basically a 4-dimensional integration routine, to a union of 4-dimensional pyramids, which are pulled back to a 4-dimensional cube. And for that 4-dimensional cube, we set a tensor Gauss quadrature rule. And 5 here, which you see in this line, is the number of the 1-dimensional quadrature rule, which is the basis of that integration routine. Okay, so you have to understand that if there's a 5 here, then we have 5 to the power 4 number of quadrature points for all of the pyramids which are used to integrate over this pair. So for a pair, I think if they are touching, we have, depending, so if it's a edge touching, we have, I think, 5 of those pyramids. So and I think 6 if they are equal. So it's like a lot of quadrature points which we need here, and setting the same number for all of them is maybe not the best way, but you can do that and obtain solutions which work with that technique. Okay. This technique is very commonly used for boundary element methods. You find very nice description for this, and of course there are much more sophisticated approaches to integrate over this. But this is the least you have to do. I mean, in order to get some result. Okay. Yeah, here just a list of singular kernels. So that would be this, I said it already, the diffusion type kernels and the paradigmatic type kernel. And there's also the fractional type kernel. If you have your new kernel and you want to make it or declare it as singular, there's again some kind of C++ map where there's a lookup of all those singular kernels. So you just add this one to your map, and then it has this behavior that in the first layer of the breadth first traversal, it can use special quadrature if you set it accordingly. Okay. Okay, then of course, if you set that, you have to rebuild everything, as said before. Okay, now the ansatz space. For the ansatz space, there are two options: continuous Galerkin and discontinuous Galerkin. And the discontinuous Galerkin only works for like constant kernels and weakly singular kernels, and in the fractional type, it only works for s smaller or equal to 0.5. That is not a technical issue. That's yeah, and that's how it is. So we have a specific another integration routine which is not called fractional. It's called weakly singular for those cases. It can integrate kernels with singularities which are weaker than s equals 0.5, and for that cases and also for all the other cases, you can use discontinuous Galerkin ansatz space. We now set in the configuration continuous Galerkin as ansatz space for us. So now we have the case that s is equal to 0.5 and we use continuous Galerkin as ansatz space. So the reasons, of course, that those functions are Lipschitz continuous. Yeah. And discontinuous Galerkin functions, they're not Lipschitz continuous. Okay, so we have set this, and now we come actually to the main part. We want to solve the system. Here we are given minus L delta U equals F on omega and U equals G on gamma. So what we do is usually, so we have this stiffness matrix A, which is defined on omega, but also we have the interaction with the non-local boundary R gamma here. And on that boundary, we know already the solution because there we set U to G. G is the boundary data. So we solve that system and we can reformulate the problem so that we get a omega U equals F tilde, where we subtract A gamma of G from F. Okay, so that is how one can do it. So this is what we do here. So we somehow set up the load vector. You can do that. I mean, this is also, there's also some functionality to set up load vectors, but of course you can do that also with your own code. And then we set the function, the vector G to the load on those labels which are belong to the Dirichlet boundary. So if the label is smaller than 0, then it's a Dirichlet boundary vertex, and then this is where we set G to the Dirichlet data. Okay, so this is the preparation here. And then the assembly happens. And the assembly, okay, need kind of, again, the labels of the solution. I show you here what happens. So we set the solution label. So that's basically the degrees of freedom. So the question is which degree of freedom belongs to the interior, which belong to the boundary. And we can, of course, derive that from the mesh and from the ansatz space and the dimension of the kernel. And then we get this solution label vector here, and then we can distinguish between A omega, so this is the first part here, and A gamma, or AD is called here, AD. This is the second part. Okay, so the stiffness matrix contains both of them. That's a CSR format matrix, and this is how we can split it up. And then, of course, we can, as seen in the formula, create a F tilde by simply subtracting that part and solve the system. Okay. Of course, here we just use any sparse solver. So again, this is a CSR, SciPy CSR format matrix. And then you can use a sparse solver with that, and you get the solution and write it into that interior of the solution. And on the Dirichlet boundary, we just put the G. Here again, okay, of course, yeah, we have to correctly derive the degrees of freedom from the mesh. Yeah, as I said, I put everything into that mesh object, so that's how it works. Here we also delete the artificial vertices so that we have better plots. And then you can, for example, see here this case with the disconnected domain. So we have the black part, which is the Dirichlet boundary, where G is 0 and F in U is 0, and the forcing term on the interior lives somewhere there on those disconnected subparts. And then this is the solution. And because there is some kind of interaction with the Dirichlet boundary, it's non-singular, the system is non-singular, and we can solve that. So that is the fractional solution for the fractional type kernel with S equals to 0.5 on continuous Galerkin ansatz space. Okay. So that's a summary. So that's another example, but basically you saw all the steps now in the presentation. This time here I chose the microelastic on discontinuous Galerkin ansatz space. So that's just the name of the configuration. That gives us some elements. We choose some kernel with the function. In this case, it would be microelastic, the diffusion microelastic kernel. We have some load here, the configuration, which contains the quadrature rules and the ansatz space. So in this case, it would contain discontinuous Galerkin somehow. And then you can run the stiffness matrix. This from array allows to simply put elements, element labels, and vertices in that, and it automatically generates the mesh with the artificial, with additional information about the degrees of freedom and everything. So it generates that information from that and also from the kernel. So if the kernel, for example, is matrix valued, for example, then of course the solution vectors are larger. Okay, and then you saw how we extracted the parts of the subparts of the matrix. And here in this example, I just put a jump into the right-hand side so we can see the jump in the solution. So that's just for an example. Now I show you if you want to do something on your own. This tutorial, what you see here, so this is a Jupyter notebook, and this is part of the repository. So if you download the repository, you find this talk. So you can execute the code. And if you pull the Docker image and run the Docker image, you can also run this code. The examples in this case are, so there are additional configurations for a disjoint case. You saw those disjoint domains with artificial vertex. There's also one with no artificial vertex. That system will, of course, be singular and doesn't work. There's this case with the hole. You saw the hole there without artificial vertex. The system is not singular, but the solution is not correct. And then there's a paradynamics example where you somehow you can deform the mesh with the solution. So there's a matrix valued case. So there's a matrix valued kernel here. Then there are two fractional type examples, one with continuous Galerkin, one with discontinuous Galerkin. And the example you just saw in the summary. So you can try this, look at it, what kind of settings there are, what you need there. And there are some plotting routines which you could also choose to look at your solutions. And here, okay, here you see the example from what I just computed. So here you see the jump, which is in the solution, which came from the right-hand side. Okay, so that was it from my side concerning the presentation. So Marta, I think we start a bit late. So how much time do we have actually?
Yes, so I think overall we started maybe around 7:15, 7 more or less. Yeah. So I would say, let's say we still have 20 minutes.
Okay. Okay. So okay, if you have 20 minutes, then I think there would be the option that if you want, we can try a hands-on session, but only, I mean, of course, only if you want. So if there's interest, you can write in the chat, and then we could together make a small break. You pull the Docker image, try to run it, and then you could run, for example, this this presentation or something else. So only if there's anyone who really wants to do this now.
Yeah, so let's do a quick survey. I know there's a way to do it with Zoom, but well, there's
already somebody who said.
Yeah. We already have a person interested. So, well, what about we try to do this?
Yeah.
And so that at least, you know, if people run into problems during, you know, just the very first steps, they can ask you right away.
Yes. Yes.
So let's try that. Let's try that.
So yeah, I would say that if you're interested, then you can go to that link which Marta posted in that non-local codes event abstract. There you find the repository, and I show you. Oh, I just share my screen, and you see it everything here.
Actually, yeah, I was about to suggest. What about exactly? It would be great if you go through the steps that people have to do. Okay,
sure. So then you end up here. That's the repository, and there's this explanation how to set up. Oh, I just make this a bit larger if it's possible. Not much better. Okay, so there's this line here. It says Docker, and then the question is it explains how to open a Docker Jupyter notebook on that port on your computer. You choose that port here. You set there, for example, 80 or something else, some number, and then you run the Docker with that address. So then it pulls the Docker image from that repository, and it will then execute the command Jupyter notebook. And that opens a Jupyter notebook on your local host on that port. So if you type then in your browser localhost and that port, double dot and that port, and then you can access the Jupyter notebook. I think maybe you will see a password thing, but you just press enter and then you're in that thing. And then basically what you see there is this. You see this whole repository, and you will then go, if you go to examples, tutorial, then you find this tutorial notebook. And that notebook is basically the presentation which you saw now. And there you find all the examples and things which I showed you. You find in data, you find all the meshes. So you could try to execute it. So that is first of all. Oh yeah, Christian posted actually the link in the chat. That's very nice. That's very nice. You can also install it yourself, but you see this is a bit more of work because you need all those packages, and maybe that's a bit tedious now. But I know that other people already tried it and it worked, so it's not impossible. Yeah.
Should we try to run a quick test, maybe, Manuel, just to see how to, I don't know, maybe change it?
Yeah, I think that, I mean, whoever wants, you can, or you want me to do it?
Yeah, why not?
I can also do it, yes, sure. Okay, then I have to share my screen.
If you're comfortable doing so.
Yes, it should work. I have to share my terminal.
Mhm.
So basically here, that's the terminal. I hope you see it. It's not very
Yes.
large.
Oh no, looks
Okay, it's
fine.
okay. Then I enter that command, which I copied from the page. And I put some port here, maybe 80. We'll see if it works. Okay, in my case, of course, I don't have to download the Docker image because it already is on my computer. So it didn't download it. The Docker run command can actually be one of the issues. So if you do not have Docker installed, then maybe that is a problem. But that is a problem with Docker. So if you Google it or if you ask me, I could help you. So that is it, basically. There was everything here. And you see already the output from the Jupyter notebook. It prints something to the terminal. So I now stop my share here and share again my browser. Share. Okay, here you see my browser. And now, as I started the, oh, that doesn't work very well. As I started the Jupyter notebook on localhost, so if I type 80 here, then it opens the Jupyter notebook. You see, I need a password here, just type in nothing, and then I'm in that. Now I entered the Docker container, and within the Docker container, this Jupyter notebook runs. So we can go to examples, tutorial, and then we can, for example, open this tutorial, which you saw right now. And then this looks as follows. Yeah, here. Okay, there are some kind of formulas, and then also you see the output there from the code. So it's the output is saved in that Jupyter notebook. Of course, if you re-evaluate it, you see it here. I can rerun the code here. Then I get different things. I could also maybe put now another name here. Okay, I need to look up the names for the examples. Let's say we take the whole. Okay, so another name would be this whole with artificial vertex, and then you see this one. Okay, so there's this artificial vertex there. Maybe we trim it away. What's the function called? I don't know. Ah, yeah, there it is. Okay, that doesn't work. Ah, let's not do it. Okay, so this is the other example, and you can maybe basically go through this. Maybe we can look at the paradynamics example. It's maybe the nicest one. Here, I think the mesh is simply a circle. Yes, it's simply a circle. And yeah, so if you choose this other example, then of course all the plots change. Okay, here this plot is the same one, but we could maybe jump to the summary and then just try out the other one. Is there already anybody? No. Yeah, maybe we just do this. Now I do it in the other presentation. That's not the Docker container, but it really makes no difference. So you see this better. So you can choose here simply another example. So for example, the paradynamics example, and then we maybe see whether it works or not. So paradynamics means that's the prototype microelastic kernel, which has a 2D output. I don't know whether it works or runs, and I do not know whether it is discontinuous Galerkin or continuous Galerkin, but we will see. So that is it. And maybe, okay, we need a different plotting routine here, of course. Let's see which one we have here. Is there something? Yes, oh no, 3D paradigms, that doesn't help us a lot. Okay, that might not help us very much. Maybe we do, let's see if that works. Okay, so that's the mesh. Good. And we could maybe change the vertices of that mesh a bit. I don't know if it works, but maybe we can try this. Maybe totally. Okay, no, that doesn't work. Okay, let me see. Okay, so here you see, for example, the deformation. So if we solve the paradigmics problem here, if you solve the paradigmics problem, then of course the solution of that is some kind of deformation, and maybe we cannot plot it very nicely, but we can of course take the vertices and then change the position of the vertices with respect to that solution, and then you somehow see some kind of deformation here. Okay, so that is of course possible. Okay, those kind of things you could try if you did use the examples. Okay, so you can just go through it, make some experiments yourself, and you also learn a bit about the configurations, because I mean we use that code for ourselves, and it has many options, but not all of them are perfectly easy to understand. So you have to go through it and explore it a bit. Okay, but I think if there are no questions, then I would say that I'm done.